everyone, welcome to the course on medical biomaterials. We will continue on the topic of hydrogels. I just introduced that topic yesterday in the previous class. Hydrogels are, as the name implies, jelly type of polymeric material. It could be a natural or it could be synthetic, and it takes a lot of water in it, and that is why they are called hydrogels. For example, if you look at this picture, the one here is a dry material, dry polymeric material, but when it takes up water, as you can see in this other picture, it swells a lot, and that is why they get the name of hydrogels. Okay. So, it is a 3D network of polymeric chains that are cross linked by chemical or physical bonding. Okay. There are bonds of chemical nature or physical, could be like non bonded interactions and so on actually, and they absorb, retain large amount of water, and there are a lot of hydrophilic groups. There are even groups which has negatively charged, okay, so they can take up cations and so on actually. So, the classification of hydrogels, we have permanent chemical bonded or reversible physical bonded. That means, when there is a physical bonding, it is reversible, that means the material can be a hydrogel by adding water, or it can give up all the water, or it could be a permanent the chemical bonding. So, chemical bonding could be covalent cross linking, equilibrium swelling, depends on the polymer water interaction and cross link density. Whereas physical, the networks are made up of molecular entanglement or secondary forces like ionic forces, hydrogen bond forces, hydrophobic interactions and so on, and the dissolution is prevented because of this. And these are all very reversible. So, when I change the physical conditions or stress, they may come back to the dry state. So, there are three types of water in hydrogel. One is called the free water, that is the water which is exactly like the water that is present in the bulk, okay, that is like a pure water. So, it will get frozen when the temperature is lowered, maybe at around 0 degrees centigrade, okay, it exactly behaves like the water present in the bulk. Then we have freezing bound water, that is the water which is weakly bound to the polymer chain, and this also undergoes thermal phase changes. That means, this also can get frozen and this also can become liquid, but generally it is below 0 degrees centigrade. Then we have the bound water non freezing type, that means the water is strongly tightly bound to the polymer. So, it will not freeze and become liquid like these freezing bound water or free water. Okay. So, the phase changes may happen much lower, you will not see a phase change also for all you know. Okay. So, three types of water present in hydrogel. Okay. So, materials which absorb water does not mean it is an hydrogel, but materials which absorb water where the water is in these three different forms, we can call this as hydrogel. Okay. Now, how do you prepare these hydrogel? We can do it by physical cross linking or through chemical process, like I said, physical. So, easy to produce, no need to use cross linking agents like glutaraldehyde or some other small molecules. Okay. So, one approach, heating cooling a polymer solution. So, when I cool hot solutions of gelatin or carrageenan, it forms a gel due to the helix formation. That means, as the temperature is lowered, these material forms helical structure, even linear glucons. Okay. When the temperature is lowered, they form helical structures. Now, these helices have junctions and crevices where the water can be trapped. Okay. So, carrageenan above this melting transition temperature, they are random coils, but when you keep reducing the temperature, they form this helical structure. So, these are rigid helical rods, so they form hydrogels. So, when you have salts present, of course, they can aggregate and they form very stable gels, because the salts will have both cations and anions. Okay. So, they form very strong bonding. Ionic interactions. So, ionic polymers cross linked by the addition of di or trivalent counter ions. So, I could add calcium 2 plus, for example. So, if we take sodium alginate, like the name implies, sodium and alginate. Okay. So, we can add calcium to that. Then when we add this type of multivalent cations, okay, it forms a gel because calcium has 2 charges, right, 2 plus charge. So, it can connect to 2 different alginate chains. Another one is complex co-acervation, okay. That is, co-acervation means we have both the anion and cation, or 2 groups of molecules of different charges coming together. So, mixing of polyanion and polycation. Polymers with opposite charges stick together and form soluble and insoluble complexes depending upon the concentration and the pH, okay, like polyanionic xanthan with polycationic chitosan. Okay. So, they have this complex co-acervation because of the positive and the negative charge. Okay. Proteins below its isoelectric point. So, we have positively charged and associated with anionic hydrocolloids and form polyion complex hydrogels. Okay. So, so you are creating this positive charge on proteins below their isoelectric points. So, I can add anionic hydrocolloids so that they form complex hydrogel. Okay. These are all ionic type of hydrogen bonding obtained by lowering the pH of aqueous solution of polymers with carboxyl groups. Hydrogen bond carboxymethylcellulose formed by dispersing CMC and HCl. Okay. So, we have both. Replacing sodium in CMC with hydrogen in acid. Okay. So, when I add sodium gets replaced by H, so it can form hydrogen bond. Hydrogen bonds decrease the solubility of CMC in water, so they form elastic hydrogels. Other examples, we have a polyacrylic acid and polyethylene oxide based hydrogel prepared by lowering the pH. Xanthan alginate hydrogel, a change in matrix structure due to intermolecular hydrogen bonding between them. So, all these are examples where there is hydrogen bond plays a very important role in creating this particular hydrogel system. Okay. Then maturation or heat induced aggregation. Okay. So, aggregation of proteinaceous components induced by heat treatment. So, when we have heat treatment, it increases the molecular weight, so that produces hydrogel. So, gum arabic containing 2 to 3% protein. So, maturation of the gum, transfer of protein associated with the lower molecular weight components to give large concentrations of high molecular weight. So, these are all heat induced. Freeze thawing. So, when we freeze and thaw, formation of microcrystals in the structure due to the freeze thaw leads to physical cross linking. So, freeze thaw gels of polyvinyl alcohol and xanthan. Okay. So, when I reduce the temperature, it forms microcrystals, okay, and that leads to physical cross linking. Okay. All these are physical based method. Now, we come to chemical based. So, physical based method, like I said, we have heating cooling a polymer solution. Okay. Then we have the ionic interaction, adding a di or trivalent ions, complex co-acervation, formation of hydrogen bonds, then okay, maturation, heat induced aggregation, and then freeze thawing. These are all physical methods. Now, let us go look at chemical cross linking. Okay. So, there we are having a reaction. So, there is a bond formation. Okay. So, that is a chemical cross linking. So, reaction of the polymer functional groups like OH, COH, NH2 with cross linkers like glutaraldehyde, adipic acid, dihydrazide, like that, you know. So, we add all these, so they react with the functional groups in polymer, because many polymer contains, say like PVA contains OH, if you are looking at acrylic acid contains COOH, and then if you look at sugars, some sugars they have NH, amine, amide, so on. So, they all cross linked using glutaraldehyde. Glutaraldehyde is very commonly used. Interpenetrating polymer network, polymerize a monomer within another monomer. Okay. So, we have a monomer, we have another monomer, then we sort of interpenetrating polymer network. So, that is a chemical cross linking. Hydrophobic interaction, incorporating a polar hydrophilic group by hydrolysis or oxidation followed by a covalent cross linking. Okay. So, I will incorporate a polar hydrophilic group and then we oxidize and then we do a covalent cross linking. Okay. That is another type of approach. Okay. So, we create in a polymer hydrophilic group by having a polar hydrophilic group, then we hydrolyze or oxidize and then we cross link the system. So, chemical cross linkers further, what do we use? We use glutaraldehyde, epichlorohydrin, these are all very commonly used, citric acid, introduction of new molecules between the polymeric chains to produce the cross linking. So, if we have two chains, in between these two chains we are putting in epichlorohydrin or glutaraldehyde. Okay. For example, cross linking of PVA hydrogel using glutaraldehyde, cross linking of CMC using 1,3-diaminopropane. So, all these are small molecules which are in between two chains. Okay. Then comes grafting, that is polymerization of a monomer on the backbone of a preformed polymer. So, we have a polymer, then we put in another monomer and start polymerizing. Polymer chains activated by the action of chemical reagents or high energy radiation. So, we activate them by putting in some radiation, or we add some highly reactive functional groups. Growth of functional monomers on activated macro radicals leads to branching and further cross linking. Okay. So, we already have a chain, long chain, we create radicals and then we create branching and then cross linking, that is called grafting method. This grafting has a chemical grafting, radiation grafting. So, in chemical grafting what do? We have a macromolecular backbone, okay. This is activated by the action of chemical reagent. So, we have starch grafted with acrylic acid by using N-vinyl 2-pyridone. Okay. So, we have starch, okay, backbone, then we put in acrylic acid using this particular chemical. So, it shows excellent pH dependent swelling behavior, ideal characteristic for drug delivery in the intestine, otherwise pure starch is not very suitable. Other one is radiation grafting, that means we initiate the grafting using high energy radiation like gamma or electron. So, when these bombard the backbone, they create radicals which are ready for chemical modification. Grafting CMC with acrylic acid in the presence of electron beam. So, the electron beam, what does it do? It initiates free radical polymerization of this acrylic acid and CMC. So, that is called radiation grafting. So, we have chemical grafting, that means chemicals modify the backbone and then it add other functional groups, or radiation creates functional groups or radicals. So, we can add another monomer and then polymerize it further. So, we have radiation cross linking, that is the third approach. Okay. So, here exposure of the polymer to high energy source such as gamma ray, X-ray, electron beam, okay, and then this leads to direct or indirect, depends on the polymer environment, solution, concentration, solid state and so on. Okay. So, what do we do? Another approach, we do the radiation, but we immerse the polymer in aqueous. So, the radiation mainly absorbed by water. Water radiolysis generates reactive free radicals which interacts with the polymer. So, you are actually radiating the water which generates free radicals, which in turn generates free radicals on the polymer. Radiation in concentrated solution, these are different approaches of this radiation, both direct and indirect. Concentration of polymer, high radiation directly acts on the polymer to form free radicals. Water is also radialized to form free radicals. Okay. These are indirect method, this is indirect method, this is direct method. Okay. These are all based on radiation cross linking. Okay. So, what are the advantages? It retains biocompatibility of the polymer as it does not involve the use of chemical additives. So, if I am using a chemical cross linker, the polymer is getting modified. Sometimes the functional groups get modified, the reactivity may modify, hydrophilicity may modify, the surface energy may get modified. Okay. And the advantage of radiation is we achieve modification as well as sterilization. So, it is very good, cost effective. Disadvantages cannot be applied on polysaccharides and other natural polymers, because polysaccharides or other biopolymers will completely get disintegrated. So, it leads to degradation. So, that is the big problem about using something like radiation grafting. Okay. So, we have chemical, we have different approaches, right. We talked about chemicals, we talked about radiation and so on actually. Now, these hydrogels, one of the most important thing is they swell, they take a lot of water. So, it can be used for skin grafting, open wound treatment. So, swelling is a very important part of this hydrogel. So, we can even put in drugs, antibiotics or anti-inflammatory molecules. so that when it releases it helps in the treatment of the burn wounds or scars and so on. Okay. So, that is degree of swelling, the ratio of the sample volume in the swollen state to volume in the dry state. Okay. So, we can look at volume or weight and then see how much change happens when as a function of time when it is put into the when it is put into water. So, it helps importance of degree of swelling, solute diffusion coefficient, surface properties and surface mobility, optical properties, mechanical properties. Although these hydrogels cannot be used in mechanical environment, force related environment, because they have very poor strength, still handling of the hydrogel is very important. So, it should be able to sustain that sort of forces. Okay. Okay, the diffusion is also very important, because when we are talking about drug uptake and drug release, the diffusion of the drugs from the hydrogel plays a very important role. Okay. Okay. There are something called zero gel and aerogel. Okay, two types of hydrogel. Okay, that is the zero gel and aerogel. This is a solid, zero gel is a solid form of gel by drying it slowly at room temperatures with unhindered shrinkage. So, we slowly try to dry the gel without any shrinkage, then that is called zero gel. It retains high porosity because you are not allowing it to shrink, and it has also got very good surface area, like silica gel dried out on compact macromolecular structures like gelatin or rubber, they all come under that. Whereas aerogel, this is derived from a gel in which the liquid component of the gel has been replaced with a gas, that is why it is called air. So, it can be any gas, it can be air or it can be even some gas, okay, that is called the aerogel. It is very low density solid because we have a lot of pores filled with the water. Okay, it can be used as a thermal insulator. They are also called frozen smoke, solid smoke or blue smoke due to its translucent nature and the way light scatters in the material, okay, like silica aerogel, they are very good at thermal insulation. So, we have two types of gels, zero gel, we are allowing it to dry without unhindered shrinkage. So, it has got very high porosity and enormous surface area. Aerogel, we have air or any gas molecules inside those voids. Okay, so, they have very low density and very lightweight, and they are very good thermal insulators. Okay. Then stimuli responsive hydrogels, because hydrogels, if they can respond based on pH or temperature or any other environment, it may be very useful if you want to deliver drugs. So, stimuli sensitive response to surrounding environment like pH, temperature, ionic strength and electric potential. Okay. So, those such gels are very good to have. So, significant volume changes in response to small changes in the stimuli. So, small change in pH, and then we expect the volume change to be very large. Okay. Thermogels, they are temperature sensitive hydrogels. That means when there is a change in temperature, these hydrogels start releasing say drug or moisture. So, physical salt gel transition as temperature changes, which is reversible upon cooling. So, this can be administered via injection using conventional syringe, and subsequent in situ gelation occurs at physiological temperature. So, we can inject a cold gel, and inside the body it can become hydrogel. So, it avoids invasive surgery for implantation. High water content improves compatibility with the injection within the injection site. So, we can target like poly N isopropyl acrylamide. Okay. This is a hydrogel which is temperature sensitive. So, this is a thermo sensitive gel. pH sensitive gels, pressure of ionizable pendant groups in the polymer backbone. So, we have a pendant group in the polymer. So, at certain pH they get ionized. So, that is the pH sensitive hydrogels. Okay. At appropriate pH and ionic strength, these groups will ionize and they result in the buildup of a fixed charge along the polymer. This electrostatic repulsive forces results in the pH dependent swelling and deswelling process, as the water is either absorbed or expelled from the hydrogen network. So, we can have for example, at tumor sites the pH is acidic. So, the hydrogel may be able to release at that particular condition drugs that has been encapsulated, or water or any other chemical that has been encapsulated. Okay. Polyacrylic acid, polymethacrylic, all these are pH sensitive. So, equilibrium swelling behavior of ionic hydrogels. So, we have these ionic hydrogels. Okay. What happens if you take a cationic hydrogel? So, as the pH is increased, so equilibrium swelling is very high at low pH because they are cationic at acidic pH, and it comes down dramatically when it goes to basic. Whereas anionic hydrogels, they have very low equilibrium swelling, whereas as becomes basic they start swelling like as shown here. Okay. These are the cationic hydrogels and these are the anionic hydrogels. Okay. So, anionic hydrogels, this one swells at pH greater than pKa, that is this side, like polyacrylic acid, polymethacrylic acid. Intestinal drug delivery to protect drugs from gastric degradation and denaturation at low pH. Okay. So, as you know, stomach or gastric pH is very low. So, we can have hydrogels, okay, like this. So, it prevents the denaturation. So, it releases the drugs in specific location like upper small intestine. For example, when it goes to the small intestine, the pH starts going up. Stomach may be 2, in intestine upper region it may go to 4. So, it may release the drug or colon or GI tract and so on actually. So, we can control based on the pH where it needs to. The cationic hydrogel, pH less than pKa here. Polymers from monomers of dimethyl aminoethyl methacrylate, okay, DM, okay, DMEAM, diethyl aminoethyl methacrylate and acrylamide. So, drug release in the stomach or intracellular environments. Okay. So, that means here in the stomach you want it to be released, so, and that is at very low pH. So, these cationic hydrogels are very good. Okay. Anionic hydrogels are very good if you are talking about intestine region or colon region. Okay. So, depending upon the pH, the anionic hydrogels will release at higher pH and cationic hydrogels will release at lower pH because of the equilibrium swelling. So, biological hydrogels, these are networks of protein polysaccharide chains that contain 90 to 99% of water, cells, tissues, organs or entire organisms. Okay. So, they can be called as biological hydrogels because they contain a lot of water. They are responsible for mechanical properties of cells and tissues. They regulate passive transport of particles and molecules. They serve as lubricants in joints or epithelial surfaces. Okay. So, what are the examples? Cytoskeleton, the cell shape, mechanical resistance to deformation. So, this prevents mechanical resistance to deformation, it stabilizes tissues. Then if you look at the ECM, extracellular matrix, mediates cell addition, proliferation, regulates the distribution of proteins, growth factors, ions and drugs. Okay, these are all extracellular material. Mucus, lining the stomach, bronchial tubes, intestine, they also take in water and can swell, serves as lubricant. First line of defense against pathogens, aids in adsorption of nutrients, alteration in mucus permeability, viral and parasitic infection. So, these are all biological hydrogels, mucus, extracellular matrix, cytoskeleton and so on. Okay. Nuclear membrane, barrier that regulates exchange of macromolecules between nucleus and cytoplasmic compartments, they are also biological hydrogels. Basal lamina, this creates an envelope around blood vessels, controls the exchange of material between blood stream and tissue, governs angiogenesis. Blood clot, even that is a hydrogel. Glycocalyx, this is the lining epithelial cells of blood vessels, highly hydrophilic, okay, that is the lining material inside the blood vessels. Sinus secretion, that is also called an hydrogel. So, a lot of biological, that means inside the body we have plenty of hydrogels which can swell and lose its moisture content, and they all serve a lot of purpose, and they all have certain important tasks to perform actually. So, what are the polymers that form hydrogel? Natural, synthetic, hyaluronic acid, sodium alginate, chitosan, okay, glucan, synthetic PVA, poly-N-vinyl pyridone, polyethylene glycol, polyhydroxyethyl methacrylate and derivatives. So, there are lot of these polymers, and these polymer moderately or poorly swollen hydrogels. Okay. They are highly swollen hydrogels, and this one is poorly swollen. So, lot of polymers. So, we always use these polymers to form hydrogels. Okay. Carrageenan forms hydrogel, I missed out that. Glucan, that is also a synthetic polymer, that also can form jelly type of behavior. So, a lot of natural polymers are there, synthetic polymers are also there actually. So, sometimes we mix them together to get the correct properties. Okay. So, applications: soft contact lenses, polyhydroxy ethyl methyl acrylate. Okay. These are used in soft contact lenses, earliest biomedical application. It increases comfort. Originally they used to use hard contact lenses, so the eyes get swollen after a couple of hours, whereas the soft contact lenses one can wear it for a very long time. Reduced adaptation time, easier fitting procedure. Disadvantages: cost hypoxia due to oxygen impermeability, toxicity and lens spoilage. Silicon hydrogel lenses more prevalent in market now, higher oxygen permeability, comfortable fit. Disadvantage: more protein deposition, so the lens spoilage. Wound dressing: hydrogels are used widely in wound dressing, moist dressing, components of paste for wound care. We can have a drug encapsulated wound dressing, dry wounds, burn wounds. So, we can have moisture donor effect, helps autolytic debrittlement, increased collagenase production and moisture content of necrotic wounds. Can absorb and retain contaminated exudate within the gel mass through expansion of cross-linked polymer chains, resulting in isolation of bacteria and odor molecules. High water content allows vapor and oxygen transmission. Cooling and hydrating effect. Okay. So, burn shield hydrogel, burn dressing, polyurethane foam containing 96% of water and 1.06 Melaleuca alternifolia extract. These are used for bone shield wound. Okay. Okay. So, lot of companies make these type of products. You can see Granugel, Intrasite gel, Purulon gel, Aquaflow, wound tab using pectin, CMC, propylene glycol, CMC again propylene glycol, sodium CMC, polyethylene glycol, polypropylene glycol, sulfonated. So, they are all used quite a lot in wounds. Okay. Deep wounds, shallow wounds, thick wounds, first stage, second degree burn wounds, okay, quite a lot of wounds. All these are products which are in market for all sorts of wounds actually. Of course, it can be used for drug delivery also. Okay. Porous structure allows drugs to be loaded and then released, possibility for sustained release. We can have different types of mechanism of release: diffusion controlled, swelling controlled, chemical controlled. Sorry, this is called swelling control, chemical control, environmental response. Topical applications used to deliver drugs to alleviate symptoms. Hydrogels made of PVA, polyvinyl pyridone containing extracts from medicinal plants for atopic dermatitis. So, lot of drug delivery examples are there. Transdermal delivery of drugs, polyurethane hydrogel as monolithic drug reservoirs. So, ocular drug delivery systems, lenses or punctual plugs, polyethylene glycol hydrogels with dexamethasone, okay, as an anti-inflammatory as well as pain reliever. These are almost reached phase 3 trials. Okay. Lot of advantages. Vaginal insert, cervidial for cervical ripening. Okay. This has been in the market from 90s, late 90s, controlled release formulation used to induce labor in patients who are at near the time of delivery. Okay. This is another example, hydrogel for subcutaneous insert in the form of reservoir system for the release of sterolene acetate. Okay. This is a hormone agonist indicated for the treatment of children with central precocious puberty. Okay. It produces decrease in a particular hormone LH levels and sex steroids within the first month of treatment. Okay. So, this is again a hydrogel used as a subcutaneous insert. So, there are already many products in the market which makes use of hydrogel tissue engineering, okay, as space filling agent, scaffolds to prevent adhesion such as biological glue, as delivery vehicles for bioactive substances, as 3-dimensional structure that organize cells and present stimuli. Okay. So, a lot of tissue engineering based hydrogels are there. This is a product 3D matrix nanofibrous and nanoporous hydrogel formed by self assembling peptide arginine, alanine, aspartame. Okay. So, they help in the tissue growth, they are non-immunogenic, biodegradable and capable to interact with cells. They are also able to stimulate tissue growth and vascularization, could be used for slow diffusion of drugs. Self assembly properties are also there, can be applied for own. Okay, so, tissue engineering advantages, we have a lot of aqueous environment, so it can protect cells, fragile drugs, good transport or nutrition, may be easily modified with cell adhesion, can be injected also, they are usually biocompatible. Main disadvantages, they are mechanically very weak, hard to handle, difficult to sterilize. How do we sterilize these type of hydrogels? Maybe difficult to load drugs and cells, then cross link in vitro as a prefabricated. So, all these are problems with hydrogel. So, most of the hydrogel applications or topical applications, little bit subcutaneous application, okay, and little bit of drug delivery systems, wound based systems and so on actually. Okay. So, hydrogels have a lot of future, especially in this particular area of applications. Okay. Thank you very much for your time.